Okay, so today we will in this week we will focus on this multi-rate digital signal processing, and I will provide the video lecture for this implementation part. Okay, because there will be a lot of gap if we will not cover in the next week. Then okay, so what is basically this multi-rate means? What is this multi-rate means? So you can see here the term multi. So multi means multiple. Okay. So we are talking about the multi rate. So about what rate, which rate we are talking about? So we are talking about the sampling rate. Okay. So the multi rate digital signal processing means multi rate, simply we can say that multi rate means multiple sampling rates. Okay. So why these multiple sampling rates are important? Because if you see the digital signal processing, we will use many applications. So in
Regina,
particular
sorry
application,
to this,
sorry,
but they are hissing sound from outside.
sorry,
Hissing like a zzz, like that.
uh-huh, that is
Yeah,
fan sound. Yeah. Now is it clear?
yeah. Now it's better, I think.
Okay, 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 okay. So multi-rate means we can simply say that multiple sampling rates, because uh, for example, if you take the example of CD, if I want to use the CD drive, so the sampling frequency, sampling rate of the CD will be different. But what will be the input to the CD, and whatever process we want to do with the CD, so that for that purpose, actually, we need particular sampling rate to do the process in the CD. So therefore, the multi-rate sampling, the multi-rate DSP is there, okay, where we can change the sampling rates, okay. So in the multi-rate DSP, it uses multiple sampling rates within the system according to the applications. Okay. So the so we can say that this multi-rate digital signal processing uh, basically deals with the manipulation of digital signals at different sampling rates. Okay. Now, uh, we can take example like the DSP, multi-rate DSP. If we take the example, the application like telecommunication or audio processing or image processing, video processing, the biomedical signal processing. So for all this processing, we will need multiple uh, sampling rates. Okay. So here this multi-rate DSP will be used. Now, the multiple DSP refers to the art of science of changing sampling rates. Okay. Now, how we will change the sampling rate of particular signal, particular digital signal. So that we will cover in this lecture. Okay. Now, the process of this converting a signal from the given rate to the different rate, it is called the sampling rate conversion. So basically, we will be doing the sampling rate. We will converting one sampling rate to the another sampling rate of the particular signal. Okay. And the system which employs this multiple sampling rates in the processing of digital signals are called the multi-rate digital signal processing system. Okay, this system is called the multi-rate digital signal processing system. The system that employs multiple sampling rates in the processing of digital signals. Okay. Now, why I should do this multi-rate DSP? Because I need to pass a data between two systems which use incompatible sampling rates. So in that case, I need to convert this sampling rate to the other sampling rate to process my data. Okay, so here this multi-rate DSP will be used. So that is, for example, like a professional audio system. Now, this professional audio system uses 48 kilohertz rate for the processing, but the consumer, the CD player, uses this 44.1 kilohertz rate for broadcasting of 32 kilohertz. Okay. Now, when the audio professional transfer their recorded music to the CD, they need to do the rate conversion from 44 to 48 hertz. Okay. So here we can use this multi-rate DSP. Okay. Now, by using this multiple DSP, multi-rate DSP, we will increase the processing efficiency, and the DSP system cost is also reduced. Okay. Now these are some applications where the uh, multi-rate DSP is used. So there are many applications where it is used, like image coding, speech coding, A to D converter, D to A converter, communication systems, signal processing, signal compression, software defined radios, like that, radar systems, sonar systems. So there are many applications, the sensor networks like this. So here this multi-rate digital signals are used. Multi-rate DSP is used. Okay, so what are the advantages of this DSP, multi-rate DSP? So the communicational requirement are less with this multi-rate DSP. The communicational requirements are less. The storage for filter coefficients are less. The finite arithmetic effects are less. Filter order requirement in multiple applications are low. The sensitivity to the filter coefficient lengths are less. Sensitivity is also less. Now, the important thing is here the effect of aliasing. Okay. So, while designing this multi-rate DSP, effect of aliasing for this two process, that is decimation and pseudo images, for interpolation, decimation and interpolation should be avoided. So this we will see in this lecture, coming lecture. Okay. So what is the effect of aliasing? So that we have already seen while in the topic DTFT. Okay. So the effect of aliasing, we know what is aliasing. Okay. Now, if I want to categorize this multi-rate DSP, so the multi-rate DSP basically involves the manipulation of signals sampled at different rate. Okay, and to sample this particular signal with the to the different rate, there are these categories. By using this, I can convert the particular signal from one sampling rate to the another sampling rate. Okay, so the first category is the decimation. Okay, so this decimation process involves the reducing the sampling rate. Suppose for particular application, if I want the reduced sampling rate, so in that case I can use this decimation process. Okay, so in this decimation process involves reducing the sampling rate of the signal by an integer factor, only by an integer factor. Okay, so decimation is often used to decrease the computational complexity of the signal processing algorithms or to match the sampling rates of different signal. Okay, so basically with the decimation, I can convert one particular signal to the reduced sampling rate signal. Okay, the second category of this multi-rate DSP is interpolation. Now, in case of interpolation, it involves the process of increasing the sampling rate. Like our above example here, I want to convert the sampling rate from 44 to 48. So in that case, I want increased sampling rate. So here I will use the process of interpolation. Okay. So interpolation is the process of increasing the sampling rate of a signal by inserting new samples between existing one. How I am increasing the sampling rate? By inserting new samples between the existing one. Okay. Okay. So this can be useful for tasks such as upsampling signals to match the sampling rate of higher rate system. Okay. So upsampling, for upsampling I can use interpolation. The another category is polyphase filtering. So polyphase filtering is a technique used to implement efficient multi-rate digital filters. It exploits the periodicity of the filter coefficients to reduce computational complexity. This is another category. So basically in our course, DSP course, we will be focusing only on the decimation and interpolation technique. Okay. So decimation technique is to get the reduced sampling rate. Interpolation technique is to get the increased sampling rate of the signal. Okay. These two techniques only we will focus. All other categories are just, I have just named out, like filter bank. Okay. So using filter banks also I can get the rate multiple sampling rate. There is a wavelet transform. Wavelet transform is a separate topic we are having. Okay, so in that topic we will see the details about the wavelet transform. So the wavelet transform is a powerful tool for the multi-rate signal processing, particularly in applications such as signal denoising, compression, feature extraction. We do image feature extraction. In that application, this wavelet transform is widely used. It decomposes a signal into different frequency components at the different resolutions. Okay, so in that particularly in that week we will see this wavelet transform in detail. There is another category like resampling. Okay, so resampling is uh, like a device, we can say a resampler. Using resampler, we do the resampling. So resampler is a device that both upsampling and downsampling uh, can be done with this. Okay, at a time we can do upsampling as well as downsampling. So it combines the functionality of upsampling and downsampling processes into a single unit. Okay. So upsampling if I want, so I will use the interpolation, right? For downsampling, I will use the decimation process, decimation technique. So this resampling process incorporates the interpolation as well as the decimation technique along with the filtering process. Okay. So for example, this is the example for resampling. So for example, to resample by a factor of 1.5, because this is only with the integers. We are doing the factorization by integer factor only. Okay, but if I want to resample some signal by a factor of 1.5, okay, so first I will do the upsampling, or I will do just the in 1.5. I can say this is 3 by 2. Okay, this is integer 3 by integer 2. Okay, so in this case, we will do the interpolate, we will interpolate the particular signal by 3, that is upsampling by 3, and then we will do the downsampling, that is decimation process, with the factor of 2. Okay, so this is the combination of both decimation and interpolation. Okay, so if we do this interpolate by 3 and decimate by factor 2, then this is basically the particular signal is resampled by a factor of 1.5. Okay, so suppose I want to resample particular signal by factor 2.5. So in that case, what I will do, I will 2.5 is what 5 by 2 I can say. So I will interpolate particular signal by factor 5 and then decimate the signal by a factor 2. Then I can resample particular signal by factor 2.5. Okay. This is the resampling process. Okay. So these are the categories of multiple DSP. Okay. Mostly we will focus only on decimation and interpolation. Okay. Keep in mind decimation is reducing the sampling rate. The interpolation is increasing the sampling rate. Okay. Reducing the sampling rate means we divide the sampling, whatever sampling rate is there, we divide by some factor. The increasing the sampling rate means we will multiply that factor, which is the integer number. Okay. Whatever we are doing, the division or the multiplication, that is only with the integer number in this case. Okay. Decimation and interpolation case. Now there are some basic devices for the sampling rate alteration. Okay. So we are having a sample and hold circuit. This is one of the very basic device for the sampling rate alteration. If you are using the MATLAB Simulink, so if I want to design some circuit, so many a cases we will need this sample and hold circuit. If the particular system, if I am designing with different sampling rate for the different subsystem in the entire whole system. So there mostly we use the sampling and hold circuit block. Okay, so sample and hold circuit captures and holds the value of input signal at discrete intervals and allow the creation of discrete samples from a continuous signal. Okay, so this is basically what we are doing. Uh, we can we can create the discrete sample from the continuous signal. Okay, so this can be a first step in analog to digital conversion. Okay, so this sample and hold circuit is the basic sampling rate alteration device. Then the second one is the upsampler. Upsampler is nothing but interpolator, I can say. Interpolation is the technique, decimation is the technique. Okay, this upsampler is a device. We are talking about the devices here. Okay, the above we have talked about the techniques, the decimation, interpolation, filtering technique, then wavelet transform, resampling, all these are the techniques. Okay, so the upsampler, or we can say this is interpolator because we are increasing the sampling rate. Upsampler. So an upsampler increases the sampling rate of a digital signal by inserting zeros or zero padding between the existing samples. Okay, so we do the zero padding between because I want to increase the sampling rate. So I need to add the samples in between the existing samples. Then only I can increase the sampling rate. Okay, so this can be done by inserting the zeros. So this is called as if I zero padding. Okay, so zero padding between the existing signals. Okay, and then applying the interpolation techniques to estimate the values of the new samples. Okay. So common method is a linear interpolation is used, cubic interpolation, since interpolation is used. Okay, in upsampler. Now the downsampler. So downsampler is also called as a decimator, where I will get the reduced sampling rate. Okay, so downsampler decreases the sampling rate of a digital signal by removing the samples from the signal. Here, what we are doing, we are inserting the samples between in the signal. And in the downsampler, we are removing the samples from the signal. This is inserting samples in the signal. Okay. So this downsampling is typically achieved by applying the low pass anti-aliasing filter to the signal before discarding samples to prevent the aliasing effect. Okay, most of the time low pass anti-aliasing filter is used to do this downsampling. Okay, so now we will look into this basic device upsampling. We will mostly target these two devices, upsampling and the downsampling device. Okay, so the upsampling or upsampler, this is the general block diagram representation of upsampler. So upsampler with an upsampling factor, suppose L is the upsampling factor and this L is a positive integer. Okay, now I am having this is the block diagram of upsampler. This whole thing is upsampler. This is the input signal to the upsampler, that is x of n, and I'm getting the output xu of n. Okay, so basically upsampler develops an output sequence xu of n with the sampling rate of L, integer L, which is positive number, positive integer. Okay, so xu of n, which is output of the sequence, input sequence, with a sampling rate of capital 8, capital L. Now the sampling rate which we are getting at the output side is L times larger than the input sequence x of n. Okay, so here we can also use the anti-aliasing filter. Okay, now in case of upsampling, what we do, we basically add the samples in between the input signal. Okay, so there is one more thing, that is zero insertion is also there. Zero insertion is also important here. Okay, so what we are having, if we look at the block diagram here, so we will be having the input signal. So input signal, this is the digital signal which we I want to do the upsampling. Okay, this is the digital signal that I want to do upsampling, upsamples. Now this is digital signal, means this is actually represented as a sequence of discrete samples. Therefore x of n is written. Okay, this is the sequence of discrete samples. Okay, now after that basically we do the zero insertion. Okay, so in the upsampling process, zeros are inserted between the original samples to increase the sampling rate. So here zero insertion process. So here one block is there, that is zero insertion. Okay, where the we are inserting zeros between the original samples. Okay, and this is upsampling factor of capital L. So according what the factor, suppose we want to do upsampling by factor L, so this many zeros we will need to add in the given signal. Okay, now to get the smooth output, we will be using this filter. This is also called as interpolation filter or Okay, or anti-aliasing filter is also used to avoid aliasing. Okay, digital anti-aliasing filter or the interpolation filter. So after the zero insertion uh, in this process, an interpolation filter is applied to smooth out the uh, waveform, output waveform. Okay, whatever we have done with the zero padding, this is zero padding process. Okay, so basically this interpolation filter helps estimate the values of inserted samples based on the neighboring original samples. Okay, and this is the output signal. Okay, so this is the output of the upsampler, which is upsampled signal with the higher sampling rate. Therefore, this up arrow is shown here. Okay, so this is the basic block diagram of the upsampler. Okay, now this process, upsampling process, uh, is implemented by inserting L minus 1 equidistant zero valued samples between two consecutive samples of x of n. Okay, if I want to design L factor L upsampling, L upsampler, then I need to insert L minus 1 equidistant zero valued samples between two consecutive samples of x of n. Okay, so the input output relation I can say like this. Okay, so we are having input x of n. What is the output? Xu of n. So I can write this input output relation. So Xu of n is equal to x of n by L, where this n is equal to 0 plus minus L plus minus 2L. Okay, and so I will be having values only at this interval. Otherwise, I will be having values of 0. Okay, getting that point? If n equal to 0, if n equal to L, n equal to 2L, so this is having the values only at this, and it is 0 otherwise. So we are basically doing the 0 padding here. Okay, so we are inserting L minus 1 equidistant zeros between two samples. Okay, so now it will be more clear with this figure. Okay, so the figure below shows the upsampling by a factor of 3. Okay, so how many zeros we need to pad between two consecutive samples? So we need to pad two zeros, 3 minus 1. Okay, two zeros we need to pad between the consecutive sequence. Okay, now this is figure, you can see from by looking at the figure, it is sine waveform. So the frequency of this sine waveform is 0.12 hertz. Okay, now if I want to do the upsampling by a factor of 3 here, so how it is done? This is input and this is the upsampled output. Okay, so here you can see between every two consecutive uh, sequence, there are two zeros are padded. Okay, first is at 0, so therefore it is 0. This is 0, 0, then two samples, 0, two zeros are padded. Then next is at this around 0.7. So this is drawn. Then again two zeros are padded. Then next sequence is drawn. Again two zeros are padded. So here we are designing the factor of 3 upsampling by a factor of 3. Therefore, After every sequence, we have padded this two zeros. Just a second. Okay. So here we can say that this is the input signal is upsampled by the factor 3. Okay. So here the zero valued sample inserted by the upsampler are replaced with the appropriate non-zero values using some type of filtering process. This is interpolation and will okay. So interpolation in detail we will see later, but just an idea what is upsampling, what is interpolator. So we can imagine like this. Okay. So similarly, the downsampler, okay, decimator or a downsampler, audible. Okay. So in downsampling, basically at the output side, we will get the reduced sampling rate. Okay. So this is the basic block diagram of the downsampler. So in a downsampler with the downsampling factor of capital M, here the capital M is of integer, positive integer always. So it will develops an output y of n. The input sequence is x of n. The output we are getting y of n. Okay. So the reduced sampling rate is basically 1 by mth of the input sampling. Okay. So this is downsampling of m. So factor with factor m. Okay. So what we are doing to get the downsampled sequence. So this is down arrow is shown with the factor m. So 1 by m fact we will be multiplying by 1 by m. Okay. So it will develop the output sequence with the sampling rate that is 1 by mth of the input sequence x of m. Okay. So for example, so this downsampling operation is implemented by keeping every mth sample of x of n and removing m minus 1 in between samples to generate y of n. Okay, so what we are doing, we are removing in between samples. Okay, suppose I want the downsampler with factor 3. Okay, so what I will do, I will keep only the third sample of x of n and the uh, 3 minus 1 that is 2 in between samples I will remove. Okay. So the input output relation, if I want to show this relation for downsampler, so I can say this is y of n is equal to x of n into m. Okay. And this n is equal to 0, 1, 2 like this. Okay. Whatever the rate like downsampling with the rate of 3. So only I will take the values of the sequence x of 0, x of 3, x of 6, like that. So in what I will, I'm removing what? I'm removing x of 1, x of 2. Here I'm removing x of 4, x of 5. Okay. So I'm removing these two samples and only keeping these samples at every third sample I'm keeping. In between I am removing this. Okay, so this is the down sampler. Okay, so here this is just an example. So we are having this input sequence, sinusoidal sequence with some frequency, this frequency. Okay, so suppose I want to do this down sampling by factor 3. Okay, so what I will do here, so only I will keep the only third factor I will keep. In between I will remove. Okay, so 0 is here as it is. Then next two I will remove. The third I will keep. Okay, the next two I will remove. Next it is shown. Next two I will remove. Why I'm removing only two? Because we are doing down sampling by factor 3. If it is by factor 5, then it will four samples I need to remove. Okay, every four sample I need to remove. So like this waveform you will get. Okay, this is what, this is down sampling. Okay, so by looking at the figure also you can say this is upsampling or downsampling. So if there are many zeros are padded, then this is upsampling. If some samples we have removed and took some samples only, then in that case this is downsampling. Okay, rate also we can find out. The rate will be the integer number only. Okay, now you can also find out the sampling period. Okay, here I have not yet calculated it, but in detailed session of interpolation and decimation, there we will do the calculation. Okay, so the sampling frequency, sampling period, or the sampling frequency. By looking at this also you can say this, for this input signal, what is the time period? So this is the frequency. The one by this frequency is the time period. Okay, this is one time period. This is original signal. Now this is down sample signal. You can see period is reduced. Okay, so how many samples is there in one time period, and how many samples are there in this one time period? You can check here. Okay, the reduced number of samples we will get in one time period, down sampling. Increased number of samples we will get in one period, one time period. This is upsample. Okay, this is, if we take the case of upsampler, this is one time period. Okay, but here you can see this many samples are there in one time period. Okay, this is upsampling. Sampling rate is increased. Okay, now this is a downsampler with the rate capital M. So I'm having input sequence x of n. So this input sequence x of n I can write like this, xa of nt, where this t is the time period. Okay, so if I want to find the input sampling frequency, that means it is 1 by time period. This is periodic signal. Okay, so if I do the downsampling, so this y of n I can write x of nm, right? The relation of input output relation of downsampler is this: y of n is equal to x of n into m. M is the downsampling rate. Okay, so this y of n, I can say this is equal to x of xa of nmt. Okay, now the output sampling frequency is basically ft dash. This ft dash is nothing but the ft divided by m. What is ft? Ft is the input sampling frequency, which is 1 by t. Or you can write this is ft dash is equal to 1 by tm. This is also, you can say, 1 by tm. Okay, or 1 by t dash, where t dash is capital T into m. Okay, so this is the output sampling frequency. Okay, if I want to find the sampling frequency in that case. Now, this is the case of downsampler. In case of upsampler, please show arrow properly. For downsampler, it is down arrow is there. Okay, for upsampler, up arrow is there. So for upsampler with factor capital L, so input sequence, I can say x of n, which is xa of nt. I'm getting output y of n. So I know the relation of input output. So this y of n, I can write xa or x n by L. I always write, but n for the periodic thing, this is nt. So xa nt by L, for n will go from 0 to plus 1 L like this. Okay, otherwise it is 0. So the input frequency, that is 1 by t, which is, I'm saying, ft. This is input sampling frequency. Now if I want to find out the output sampling frequency of this upsampler, so this is L times ft. Okay, here it is ft by m. Okay, here L times ft. Okay, and ft is what? 1 by t, or I can say this is L by t. Okay, this is 1 by t dash. If I want to find t dash, so t dash is nothing but capital T by L. So like this, I can find the sampling frequency of upsampled output. Okay, so the basic sampling rate alteration devices are the upsampler and the downsampler, and they are linear but time varying discrete time systems. Okay, they are linear but time varying. So we will illustrate some properties of the time varying downsampler, upsampler, and the downsampler. Okay, so the time varying properties of this, uh, I think we will do this properties tomorrow. Okay, because if I start this now, it will take another half an hour. Okay, so we will say this properties tomorrow. Okay, for today we will stop here. Yes, student. Is there any doubt related to multi-rate DSP?
I don't think there is any doubt, doctor.
I just noise is coming. Okay. Okay, so we will stop here today. Okay.
Right, doctor. Hi,
Thank
doctor.
you. Thank you, student. Tomorrow at 10, we will be having session at 10, no? Tutorial session?
Okay, doctor. Sure.
Yeah. Okay. Please join on time. Yeah. Thank you. Have a good day.
Right, thank you, doctor.